only reality is dependent upon us. He's looking at it backwards. That's the point. But the problem would be is the only way you can disprove Bohr's stance is by using a reality that he's not even subscribing to. You know what I mean? Like he's not subscribing to the fact that these laws regulate the universe. He's saying that the universe is dependent upon us, basically.
Look,
You can contradict against Bohr, but only with the ideas that Einstein has, basically, like the reality that Einstein subscribes to.
Yeah, I brought up this exact same objection, like I think yesterday. I know it was yesterday.
Now, and the reason why it won't ever work is because unless someone's able to prove or disprove objectiveness of like the universe, then it's no way to hold either or stance as like, you know, true.
So
yeah.
So Bell's test comes to show that Bohr is definitely correct. Einstein is definitely wrong. Reality definitely does not exist until we observe it. The moon.
How do you know that?
I mean that's Bell's test. I mean if you try to reproduce the results of Bell's tests, you'll fail.
Explain Bell's test to him, because I was trying to do it.
I mean,
that's more than one test anyway, isn't it? Like a bunch of tests. It's not just like one test.
There's many tests that you can perform. I've been trying to write Python code to reproduce the data of the experiments, and I'm unable to reproduce the data of the experiments. Anyway, but first we need to understand the EPR paradox, Einstein's paradox. So Einstein said, let's prove that Bell's test. Sorry, no. Einstein said that
Bohr's ideas about it.
No. Bell is 1964. Right. Einstein died. Everybody died before Bell published this test. So Einstein never reacted to Bell. Einstein can only react to Bohr. So Einstein and Bohr reacted to each other, and many years, like I think 10, 20 years or 30 years. Yeah, 30 years after the EPR paper, Bell published his paper in 1964. So it's 29 years after the EPR paradox. Anyway, so Einstein said, let's prove the least I can do, or the most I can do, is prove that Bell's view of the universe violates the speed of light. And if it violates the speed of light, it violates the laws of nature, and we know the laws of nature are correct. So it must be. It must. No.
I don't think so, because I think this is a perceptive based argument. Like the speed of light is a perceptive based argument usually too.
What do you
like
mean?
When we say we see something 1,000 light years away and it takes a certain amount of time to get to our eyes and stuff like that, that's a perceptive based argument. So but you could continue real quick. I want to just see where it goes. My bad.
No, I mean, it's important to first understand that the speed of light seems to be a law of nature. That nothing seems to be able to move faster than light. Like in particle accelerators, when we try to push things faster than light, we're unable, because as things get closer to the speed of light, their masses grow to infinity. So you can never push even an electron beyond the speed of light.
Okay.
So all that we've ever measured is things moving at the speed of light. We've never measured anything moving faster than light. So there's, as far as we know, it seems to be a law of nature that nothing can move faster than light. Einstein predicted that as we try to push something closer to the speed of light, its mass will grow to infinity. Therefore, it should be impossible to push anything beyond the speed of light. And we know that this is correct. We've tested it. Experimental physicists have proved that this is correct. Anyway, so there seems to be a law
How
of
did they
nature.
prove it?
What?
Well, we don't got to go through that. I was gonna say how did they prove that, but we don't got to go through that. That makes me think of a black hole though. But go ahead.
Why does it make you think of a black hole?
Because that mass becomes infinity. So, I would guess that a black hole probably mass is infinity and it's just collapsing on itself or something.
No, in a black hole, the density of a black hole grows to a point where light cannot escape. It's
Exactly.
it's the density. The mass of a black hole is the same as it was before it became a black hole. It didn't gain mass.
So why is it that when you pass the speed of light, you gain mass and not density?
Wait. So as you're pushing something closer to the speed of light, it gains mass. I don't think Einstein explained why.
I wonder what if it just becomes infinitely dense?
No, you don't need infinite density. So a black hole is not necessarily, it's not infinitely dense. It's just that if you take, let's
How do
say,
you know?
you don't need to. I mean, you just don't need to. If you just look at Newton's equation, F equals gmm over r squared, right?
Hmm.
So as r goes to 0, you're dividing by something that is close to 0, the force becomes infinite, right? As the radius, let's take the Earth.
Hmm.
So compress the Earth into a grain of sand. So its radius is like 1 millimeter. So the force, right? F equals gmm over r squared. You're dividing by a tiny number. You're getting a very you're getting a very high force, a very big force. And
Would you say a black hole has high force or no?
I mean, it's a gravitational force. So that gravitational force, I mean, but the force acts equally on everything, regardless of their mass. So it's actually, I mean, we would need to go through, the derivation, but it's you don't have to think about the force. I mean, you actually, instead of thinking about the right, because you say that the force equals gmm over r squared, but F equals ma as well, right? Do you know any physics?
I took physics class. I know the F equals ma, but I don't remember
So all you need to
that
know is
much.
F equals ma and F equals gmm over r squared. So the m shows up on both sides of the equation.
Yeah.
Anyway, we don't need to go through black
Okay. Yeah.
holes.
Let's get past that real quick. Yeah. Let's go
Yeah,
back to the.
yeah. So it doesn't have anything to do with black holes.
Yeah. I just threw that out there with the light thing. But continue. We're talking about how it violates light.
Yeah, as far as we
Yeah.
know, nothing can go faster than the speed of light. We've tried pushing things, and Einstein predicted, and this is what we discovered: we cannot push anything past the speed of light. and
Mhm.
no signal can travel faster than light.
Right.
We measured, and everything travels at the speed of light maximum. Anyway, so Einstein said, let's show that if we assume Bohr's ontologic superposition, then we have to violate the speed of light. So this is the EPR paper. E stands for Einstein. EPR it's an acronym of the people that wrote the paper. So it's Einstein, Podolsky, and Rosen. So
Why does it violate the speed of light? I mean, violate. Yeah.
yeah, right. That's the whole point. The EPR paper shows that if we assume Bohr is correct, then we have to give up our notion that the speed of light is the maximum speed of the universe. This is also called
And why?
what?
Well, how come?
Yeah, let me just say this is also called locality. The notion that the speed of light is the maximum speed, that's called locality. That's just the name that they gave it, basically. That any signal that you send me can only travel up to the speed of light. It cannot travel faster. Anyway, so the EPR paradox says that Bohr's position violates locality. So how does it violate locality? So what's the EPR paradox? So I'm gonna tell you a version of the EPR paradox, not the original EPR paradox. A version.
Wait. Before you do that,
Mhm.
you're saying that it violates locality, right?
Yeah.
Which makes sense.
How does it make sense?
Kind of. It kind of makes sense.
Why do you say that?
That it does violate that, because if he's saying that what we see is the reason why it exists, then when we're not seeing it, it doesn't exist, right? So I don't know if it violates it, but it definitely changes it. He's saying that what we see only has locality when we see it.
Locality, right? So what you're saying actually makes sense. You're saying that, for example, the moon is not there when I'm not looking at it.
Looking, yeah.
But when I look at it,
But when I'm looking, though, yeah,
instantaneously it shows up, which is
right.
right. If it's instantaneous, so the moon is reacting to me faster than light because it's very far. The moon is like 1 second light. It's a light second away from me, and if I look and it's there, well, it's
You're saying it's reacting at too high of a speed to
yeah,
make sense
yeah, and
to how fast.
that's the moon.
So this is the
But
right. Okay, let's keep going. Let's keep going.
that's the moon. The sun, the same thing you should be able to say about the sun. The sun shows up when you look at it. The sun is 8 minutes away. And when you look at the Andromeda galaxy, that's like a few million light years away. And when you look at, the other side of the universe, that's billions of light years away. And these things, the universe shows up instantaneously when you look at it, but it's reacting. It's not there when you're not looking. It's only when you look
Right.
at it, which is, I mean, and I'll skip to the end again. Bell proved Bohr is correct. So if Bell is correct,
okay, continue.
right? So if Bohr is correct, then the simplest explanation is that we live in a simulation. That's not reality. This is also called realism and anti-realism. The notion that something exists only when you observe it, that's called anti-realism. So Bohr's position is not local, it's non-local, meaning it violates the speed of light, and it's anti-real, it's anti-realism. It says
I don't think I think it violates the speed of light as being the fastest thing, but it doesn't technically violate the speed of light existing. You know what I mean?
it's not so clear about the speed of light. It's not so clear because you cannot use Bell's paradox to send a signal faster than light. Even though Bell's words in
Yeah.
in Bell's words in the conclusion of his own paper, he says there must be a mechanism whereby the setting of one measuring device can influence the reading of another instrument, however remote. Moreover, the signal involved must propagate instantaneously. This is terminology that is in complete violation of Einstein's relativity. Because in Einstein's relativity, there is nothing.
Yeah. I think it definitely violates some claims about relativity for sure. Like I said, like the speed of light being the fastest thing, it definitely violates that. Because all he's saying is that your perception of the universe is faster than the speed of light. Basically, he's saying that what
But
you see
but you cannot
when you see
send.
things appear.
Yeah, but you cannot send a
Uh,
signal faster than light. The fact that the universe reacts instantaneously, this reaction, that's also called the collapse of the wave function. So this,
I agree. Now, can we lie? I completely understand it. I get the idea that what he's saying cannot operate with Einstein's theory of relativity. Like I get that.
no. So people say, no, so actually, Bell's or Bohr's position actually doesn't. There's a guy, he said, Bohr's position violates, you could say it violates the theory of relativity. It violates the spirit of the law, but not the letter of the law. So you cannot send a signal faster than light by using Bohr's position. You cannot you cannot use this collapse, this instantaneous collapse of the wave function. It ends up that you can never use it to send signals faster than light. It doesn't help you. It's just that you realize that's the way the universe works, but you can never use it, which is which is
Yeah.
which is bizarre, because you would expect, if Bohr's position is correct and the speed of light can be violated and signals travel instantaneously across infinite distances, then we should be able to use it. But it ends up that we can never use it. So there's a
Yeah.
physicist, there's one physicist, he says that's a hint that Bell's paradox is incorrect. Something is wrong. If Wait, who did we lose?
She's back. She's back.
Oh, all right.
Wait. So let me say this.
Mm-hmm.
The only reason why we see the moon is because of light, right? The only reason why we observe is because of light, right?
I
In
mean,
Bohr's
not necessarily.
explanation, it can still be the fastest thing. It's
No,
just that.
it's not necessarily the light. It's also the gravity, right? The moon causes the ocean tide, for example. So it's not just the light, it's also the gravitational field of the moon that interacts with us. So the way you observe the moon is
Right.
not just with the light of the moon. But what did you want to say?
I was gonna say the speed of light could still be faster than everything else. or what if the speed of light was the exact same speed as you observing the moon when you look at it? You're right. It wouldn't be useful to. I don't think it would be useful to. It probably wouldn't be useful, but
No, but the prediction of quantum mechanics is, and this is the test. People have tested Bell's tests, and
Right.
and Bell's test is to prove that Einstein is wrong and Bohr is correct. And they tested it in such a way that it's faster than light. They
okay. So can we what's the now? Let's get to the test then, because that's
okay.
what.
But first we need the EPR test, the EPR paradox, the EPR test. Anyway, so, and that's going to lead us to Bell's test. Anyway, so the EPR paradox is that we're going to take a particle and wait for it
Mhm.
to decay into two particles. So in general, particles, if you give them enough time, they decay into other particles. And sometimes you can get a particle to decay into two particles, let's say two electrons.
Mhm.
And but it's a particle and an antiparticle. So it's going to, so whatever was the original particle, let's call that the parent. So the parent particle will decay into an electron and an anti-electron. An anti-electron is
Mhm.
also called a positron. It's actually an electron with positive charge. It's antimatter.
Yeah.
This has been observed. We've been able to create these things in the lab. You can do it at home. Basically, it's very straightforward. You have to wait a long time, but it will happen. So there's YouTube videos of people creating these things. Anyway, so an electron always spins, and a positron also always spins. But the parent particle, let's assume it did not spin. And an electron has a certain mass. So in order for the electron to spin and for the positron to spin, they must spin in exactly opposite directions in order for conservation of angular momentum to be maintained. So are you familiar with angular momentum?
Nope.
So you know how a ski like a ski dancer, you know, the girls that dance on the they dance on the ice skaters.
Yeah.
You know how they spin, and they spin with the arms out, stretched out, and then they pull the arms in, as they pull the arms in, they spin faster and faster.
Yeah.
Have you ever seen that?
Yeah. I've seen it before.
Right. So why does that happen? Why does a ice skater spin faster and faster as she pulls the arms in?
Mm. Because
Anyway, but because there is a law of
I don't know. Just tell me.
yeah, there's a law of nature. It's called conservation of angular momentum. So,
Right.
are you familiar with just momentum? Have you ever heard of
I
momentum?
get the idea. Yeah, I know what momentum is. I get the idea though.
Right. So like
Two particles spinning, electron, positron, opposite directions. I get the
exactly.
idea.
Okay, good. So they're spinning. So they must be spinning in exactly opposite directions. However, we cannot know in what direction they're spinning. They're too small to observe. So we cannot see the spin of the electron. But
Right. And what makes us think they have to be spinning in the exact opposite directions to maintain what?
no, that's a given. We're going to be using everything I'm telling you now. This is all in order to set up the EPR paradox.
Okay.
And then we're going to talk about, and then Bell, we're going to continue talking about the same setup in Bell's paradox. Anyway, so we're assuming conservation of angular momentum, which means that assuming the parent particle was not spinning, therefore the electron and the positron must be spinning in exactly opposite directions. So if you look at them, let's say one is spinning clockwise, the other one must be spinning counterclockwise, for example.
Right.
And since they have the same mass and the same size, everything else about them is the same except for the charge. But since everything about them is the same, therefore the spinning, their spin is identical except for it's in opposite directions. Now, so because an electron is so tiny, we cannot see that it is spinning. The only thing we can do is we can have it interact with a magnetic field, and it will react to the magnetic field, and then we can know something about the direction of the spin. So a spinning electron is basically a little magnet. That's like it's a law of nature. That's basically how electromagnetic engines work. So, but there's nothing strange about that. A spinning electron and a spinning positron create magnetic fields, are actually tiny magnets. Actually, when you have a magnet on your fridge, it's a magnet because internally there's tiny atoms, and each atom has electrons spinning. And because they're all spinning, they're all aligned. So it has a magnetic field, and it becomes a magnet because of those spinning electrons. So a spinning electron.
Does it have positrons too?
What?
Does it have positrons too on the magnet?
No, there's no positrons. There's no free positrons in our universe. Our universe has matter. It has almost no antimatter. You can create antimatter, especially in a particle accelerator. We can create antimatter, but in general, and you can observe it. I don't remember exactly how. I think if you have like uranium decaying, you can observe positron or something. But there are no free positrons in our universe. Anyway, it's fine. So we have so an electron is a little tiny magnet, and so is a positron. So if you remember how a compass works, right? A compass aligns with the magnetic field of the planet of Earth, right?
Right.
So an electron also aligns with the any magnetic field that you impose on it. Anyway, it's gonna get really complicated. Are you sure you're up for this?
All right. How long is it gonna take?
I mean, you can watch videos. I can send you links of videos that maybe they can like, because I'm talking to you like in words, and they actually have animations, so you can watch the
No,
animations.
look. Okay, I just want to get to the part where uh
Anyway,
we get to the experiments. The experiments.
yeah. Anyway, but okay, let's continue. Anyway, so a spinning electron is a tiny magnet, and when you put this tiny magnet in a magnetic field, it so happens to be that it could either go up or down. You could set up an experiment with a magnetic field such that a spinning electron will either go up or down.
Right. So if
And
it's spinning in the opposite direction, it goes towards it. If it's
we
spinning
don't
in a
know.
different direction, it goes.
We
Oh, we don't
actually
know which way.
we
Okay.
don't know what causes. We only know that 50% of the time the electron goes up, and 50% of the time the electron goes down, and the same goes for the positron. 50% of the time it goes up, 50% of the time it goes down.
Okay.
But
How do we know?
mhm.
Okay. Okay. Cool.
but
Let's
what
let's
yeah, but what we do notice is that they always go in opposite directions.
the
So
electrons.
the electron and the positron, when we put them in a magnetic field, they all
They go
one
in opposite
always
directions.
goes what?
I get what you mean. They're always spinning in the opposite direction
No,
every time they're in the
no,
magnet.
we don't know how they spin.
Or they go away from each other.
They one goes if one goes up, the other one goes down.
Ah, okay.
That's it. So, but this happens 100% of the time. They always go in opposite directions.
Right.
How do you explain that?
I would assume that the electron in I would assume that the positron is giving off some type of like force that's opposite to the electron, and it just pushes it away.
Yeah.
Like you would put a magnet. If you put the same side of a magnet to the other side, it won't let you put it together, like something like that. You know what I mean?
Okay, so look, internally, I mean, why does a magnet stick to the fridge? The magnet sticks to the fridge because there is an interaction. There is a photon interaction. The magnet, a spinning electron emanates virtual photons. I mean, there is that's literally quantum mechanics. It's quantum field theory that explains why.
Okay, can we talk about why is it that when you put two matches together
The
in a
que-
certain size,
the question is
it doesn't go together.
the
It
que-
comes apart instead.
the question is
Something.
how do they know to always go in different directions? That's basically Bell's paradox. And
Why do they have to know? Why do they have to know? Why is it?
so that's a good question. So they have to know, and that's basically Bohr's position, is that they communicate instantaneously. So if you put them both in the same magnetic field, then you can come up with a simple explanation.
Right.
But what we discovered is that when we put one of them in a magnetic field that is, let's say, up and down, that forces the electron to go up and down, and you put the positron in a magnetic field that is not exactly up and down, it's just a little bit off, what do you expect it to do then?
Change the trajectory of the electron, or vice versa.
Right. So it goes up and down relative to the magnetic field. Whatever the magnetic field, the up and down of the magnetic field, that's the way it goes. But let's say the electron goes up relative to the magnetic field. What do you think the positron does relative to
Down.
Right, but I'm telling you that the magnetic field of the positron is not aligned with the magnetic field of the electron. It's a little bit off. It's like 1 degree rotated. The device that creates the magnetic field around the positron, that device, those magnets, I rotated them by 1 degree. What do you
Right.
think happens?
So let's say the positron's magnetic field is more diagonal
Yeah,
than
exactly.
the electrons are straight up.
Exactly. By just a little bit. Well,
I would say the same rules apply. The electron will want to go up, but the positron will want to push it diagonal down.
Let's assume
So we ran.
Let's assume we ran this experiment and the electron went up. Now, as long as the 2 magnetic fields were aligned, so whenever the electron went up, always the positron went down. But now that
it's only if they're aligned, but
exactly.
then now that they're not aligned, they don't work the same. Well, how would it work then? What would work?
So it's 99% of the time the positron goes down, and 1% of the time it goes up. And if you change it by 1 more degree, then it's going to be 98% that it will go down, and 2% it will go up.
Okay, I see what you're saying. Right.
And this,
how do you know that though? How did they figure that out? Like, what did they run it 100,000 times?
It's times? That's literally Bell's.
How did they measure the odds?
That is the output. When they say Bell's test, that's the output of Bell's test. That's literally the output of Bell's test. I'll show you the graph right now. 1 second.
I don't know about that one. I mean,
yeah. What?
Yeah, I don't know about that because I don't know how he's measuring 98% of the time it's gonna happen, and the 2%. Like, I don't know
that. The red line.
What test did he do?
The white. Do you see in the side chat the picture in the side chat?
Yeah, I see it.
So the white dots is the data. So this is the positron. What we're looking at is the positron. So the bottom says measurement direction. That's the measurement direction. That's the magnetic field. That's the device that creates the magnetic field for the positron. 0 means they're aligned. That the positron device magnetic field is aligned with the electron's magnetic field. That's 0. So at 0 and 360, the devices are aligned. The positron's magnetic field and the electron's magnetic field are aligned. At 180, the devices are in opposite directions.
Right.
And on
so they both go in the same direction when the devices are in the opposite direction. Or they both percentage in a direction.
No, but this graph is only for the positron. This graph is only when the electron went up. So only in the tests that the electron went up, did we look at what the positron is doing?
What about when it went down? It went down too, no?
Then it
The
would
blue
just
line is the electron?
it would just be the opposite. It wouldn't impact the discussion.
Yeah.
Anyway, so the white cubes, the white squares is the data. So what I told you that both were aligned, that's at 0, and on the left it says percentage in that direction. That means how many positrons went up. So we know that the positron in the beginning no positron went up because the electron went up. So it's 0.
Right.
So at 0 we have 0. And at 360 we also have 0. And at 180, when we rotate the device to 180, then the positron is always going up. And the question is, so the data is the white squares. And all you have to do is you have to tell me how does the positron know to behave this way? How does the positron know to give us this output?
I don't think the positron has knowledge. I think that's just what it is.
Fine.
That's how it operates. Why does it matter?
If you can explain to me how it does it without knowing, it's like
It's just so.
it's
Okay.
it's more than a Nobel Prize. It's all the Nobel Prizes combined. If you can explain the red line of the white cubes, that's all the Nobel Prizes ever
Okay, I'll
combined.
say this. The problem with that is that you will have to explain objective reality. That's all this argument is.
You have to tell me how the positron knows to behave this way. How does the right? I told you we shifted the device by 1 degree. That means we moved
Right.
just a little bit to the right from the 0. And the positron knows that instead of 100% of the times to go down, it only goes down 99 out of 100 times. How does it know? How does it know? How?
How does it know to change the percentage?
Yeah. How does it know? It
Because
sounds
of the magnetic field, the conditions. Because the shift in the magnetic field.
Look, so
No?
I mean, let's.
Because if what else would give it an indicator other than the change in the circumstance? Like there's nothing else to give it an indicator. And the reason why I know is that you're asking how does it know to operate in a certain way, like a consistent like it has a consistency to it, I guess you could say. And I would say that's where you don't have an explanation on either end. I don't think, because the only way you would know is if like God told you, or if you understood the universe objectively, you will understand why a positron could tell you. I mean, could know to shift that exact amount when you move it that exact amount. Like it's not something I could just say, why does it know that? I can't, there's no mind to read from a positron.
Right, but when you
why does water not stay clear when you put orange juice in it? It's not, it doesn't have it doesn't know to change color. It just does operate like that.
Yeah, I agree. But what's your major?
I'm not in college. I dropped out. long time ago.
What was your major?
I was undecided for a year, but I was like taking psychology classes.
Hmm. Have you ever taken any programming?
Nope.
Anyway, so are you watching? No, you're not watching. Let me show you my
Wait,
screen.
how come you? Why are you relating it to programming? What about the programming
Because
are you trying to relate it to?
I'm trying to write a program that emulates the positron. I'm trying to think
Right.
of what I'm right. I'm telling the positron what I know.
Mm-hmm.
Oh, entropy left. Okay.
Yeah, she had to go to or her house or something.
Hmm.
Yeah, you're trying to. I know what you're trying to do. You're trying to create a program that explains why the positron does what it does. But all you're going to end up with is results, right? Like you're not going to end up with an explanation of why. You know?
Um. Wait. How did I get this? Uh,
Wait, what solution do you want? One more time.
oh yeah, this is fake. Um.
Oh,
Yeah, this is fake. I asked ChatGPT to write the code to stretch it.
mhm.
So
Wait, what are you looking for in the?
I'm
What are
tr-
you looking for again?
I'm trying to recreate. I'm trying to recreate.
That graph, basically.
Yes, exactly. The red line.
Right.
That's what I'm trying to recreate. So what should I tell? So I'm trying to tell the positron. I'm giving the positron the input, of what we know. So
Mm-hmm.
this is this is where it all comes down to. So this is called the measure. This is the measurement. This is when we measure the particle. This is the particle. So here is where we measure it. And all we're telling it is the angle at which we're testing it. The angle of the device. The angle of the magnetic field in which the this is true both for the positron and the electron, by the way. They're just they're spinning
Yeah.
in opposite directions.
Right.
And when I create, this is the initialization of the particle. So in its initialization, I give it its initial angle, the initial spin angle, and I save it as the hidden angle. So
Mm-hmm.
so when I create a particle, I save its angle. So in the beginning, I create particle A and particle B. And particle
Mm-hmm.
A has angle A, which is some random angle between 0 and 360. And
Right.
angle B is just angle A plus 180. It's just it's the opposite, right? So that they have opposite spins.
That's where it would be at 100, right?
What?
On the graph, that's where it would be at 100.
No, 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 no. I'm creating two particles, particle A and particle B. And I'm giving each, when I create particle A,
At the 180.
yeah,
How
it's
come?
one, oh yeah, it's 180, it's not 100. So particle A and particle B are pointing in opposite directions. So angle A,
Right.
so angle B is exactly 180 degrees from angle A. And then I use angle A to create particle A, and I use angle B to create particle B.
Right.
Now this random, that's something that I was testing, so let's ignore it. Let's remove this random. So we're going to be creating two particles, and only if particle, we're going to be measuring particle A always along the 0. 0 is up and down. So we always measure particle A. We're always asking, is particle A measured up? Is up A? And only if particle A is up are we going to conduct the experiment with particle B. We're going to measure particle B in 360 degrees. We're going to measure it in every angle. And we're going to collect
Right.
the data. And this is going to be random. So when we measure the measure function, measure, it's going to use a random number. Let me just fix it to how it was before. So this is random, and there's no rand here, and there's no rand here. Oops. I think that's it. So we're going to run the particle. We're going to run the test. And this is what I get. It looks good. However,
Yeah, it looks similar.
it's similar. But as you can see, it goes up to 0.75 and it goes down to 0.25, which is terrible because it needs to be 0 at 0 and it needs to be 1 at 180. And it's not. It's 0.75 at 180. Which is the problem. It needs to be right. So you need to tell me,
And you're
okay,
telling me, oh, yeah. Okay, so now you're telling me this, right? But for some reason, when it operates, when we do this experiment in real life, it's always like the graph in the side chat. It's always at 0, 0, and always at 100, at
well, I
180.
can't
I
hear
mean,
you.
it's like, can you hear me?
Yeah.
I'm saying you're telling me that when they do the experiment in real life, it always starts at 0, 0, and
Yeah.
at 180, it's always at 100.
Yeah.
But when you try to run an experiment through the AI or like a ChatGPT or coding, it never brings back the exact same results. It brings like an imitated version of it, like, but not accurate.
It's right. It's different.
It makes the same
Shape.
trajectory, but not
Yeah.
with the same calculations.
Yeah. So
good question.
so all that we need, all that we are able to change is here. We cannot change anything in the code except for this. This is how the positron and the electron react. So all they do is they calculate the angle difference between their own spin and the magnetic field. It's the difference between the angle of the magnetic field and the particle's own spin direction. So this is
maybe you must tell it that it has to start at 0.
You can't. This, by the way, it flips a coin. Every time you ask a particle to measure itself, you're asking it, is it up or down? It flips a coin. This is a flip of a coin. It does a calculation.
Right.
It does this calculation. It uses the sine squared of half the angle. It's called the sine squared of half the angle. That's the probability up. But then it also randomizes it.
Maybe that's the problem. Maybe In reality, it's not random. Randomized.
No. So we know that half the time the electron goes up and half the time the electron goes down. Half the time, each of the particles, half of the time they go up and half of the time they go down. That there's no question about.
Mm.
We know that this is what the data looks like. The data is probabilistic. That's the nature of that's nature. Nature is probabilistic. That's not the problem. The question is, what is the logic that an electron goes through? What is the logic? What is the internal logic that recreates the red line?
I would say it just has to do with it being relative
What do you mean relative?
to the electrons magnetic field, because like
What do you mean? I don't understand. This has to be true for the electron, but this is the positron.
yeah, I know.
The electron always went up. When the electron went up, we ran the test for the positron in a different, and we changed the direction of the device, of the magnetic field. How do
I
you
don't know why.
what?
I said I don't know. I don't know.
It's not just that we don't know, it's that when you think about it, if you take the time to think about it, it's impossible. It's not
This
just
chart right here is impossible.
it's impossible unless we live in a simulation. These white squares, the only way it's true
That
is
they would react the same way every time is if we live in a simulation.
this data implies we're definitely, the simplest explanation is we live in a simulation.
Yeah.
The simplest explanation is
And do you agree?
I'm beginning to agree. I'm beginning to give up because I've given it a few weeks, and every genius who's faced this came to the same conclusion that reality is not real. They gave a Nobel Prize for this. So reality is not real.
So why is it that you can't do it in the coding?
I mean, the only way I can do it in the code is if I tell the particle.
I think there's an algorithm to the universe, but
they are far apart. The positron and the electron, you have to think, once they are created, we send them each to a different. They sent them to a different building. They ran this experiment not with electrons, they did it with photons. It's very similar. They sent them to separate buildings across the city, miles apart, and they ran the measurement simultaneously. So there was no time, according to the speed of light, there was no time for the particles to collude. The only way they could collude is if they are entangled, if they are literally, if they share the wave function so that they both decide at the same time what to do. So if both of them decide at the same time what to do, yeah, you can reproduce the graph. But then you've given up on reality. Then the moon is not there when you're not looking. I don't exist when I'm not talking to you.
When I'm not looking.
Yeah.
Or when you're not talking to me.
Yeah. Between each consonant, I I get smeared. My existence gets smeared across the entire universe.
I need to look into this because
This
it's pretty interesting.
yeah.
Well, what makes you start to agree with the?
Because I'm unable. It's not just that I'm unable to write the code. The code is the easy part. I'm unable to come up with with a theory that explains this behavior. I'm unable. Like I've been trying. I have a piece of paper. I mean, there's also I can show you. No. Every time it goes back to unable to launch.
Why?
Let's
I could probably launch it. Maybe. Let me see. Oh no. Maybe. Let's see.
No, I did something. I confused it.
There you go. Okay, don't pay attention. Wait, what is it? Wait, this is yours.
So yeah, this is basically it. So this is the electron and this is the positron. On the left is the electron, on the right is the positron.
Wait, where are we at? Which part?
You can look at my screen share.
Oh, stream.
Yeah.
Okay.
So on the left is the electron, on the right is the positron. So you can come up with a theory that says that the electron, so an arrow means that it's spinning, like when you want to say
that direction.
What?
It's spinning in that direction that the arrow's pointing, right?
Yeah, but it's you curl your right hand around the arrow with your thumb pointing in the same direction as the arrow, and the way your fingers curl around the stick, that's the direction of
Is where it's spinning.
that's the rotation.
I got you.
That's what the arrow means. It's called the right hand rule. Anyway, so the electron is you can come up with a theory that says that if the electron is pointing anywhere towards the upper half of the universe, then we will measure it as up. Always. But because it randomly spins, when the electron is created, it spins in an arbitrary direction. That's why 50% of the time it's going to go up and 50% of the time it's going to go down. But internally, we can never see this. This is impossible to see. But because internally it is spinning up, we'll measure it up. As long as it's spinning in the up towards right, it's pointing at the upper half of the universe, we measure it as up.
Okay.
Now, every time an electron spins in this direction, an electron is particle A. Then particle B spins in the opposite direction, exactly along the same axis, but in the opposite direction. So, so if the electron points at the upper half of the universe, then it's guaranteed.
Positron is at the bottom half.
Exactly. And that means when we measure the positron, it's always going to go down. Anytime the electron goes up, the positron will definitely go down. Okay, sounds fair. But now let's start rotating the magnetic field around the positron, right? So the magnetic field for the electron is up and down, But the magnetic field for the positron, we're going to start rotating it by 1 degree, 2 degrees, 3 degrees. We're going to start rotating the magnetic field.
Right.
And
that means at some point in time, the positron should be up while the electron is up.
Yeah,
right.
We know
But
that.
that wouldn't make sense.
Yeah, we know. No, we know that when the magnetic field is exactly upside down, then the positron always goes down, but down with the magnetic field is actually up.
Okay.
So when the magnetic field points down, then the positron is going to give us up 100% of the time. And that's what it says. That's what this says. This says that at 180, the positron is 100% of the time up.
Right.
All right. Sounds fair. But let's talk about the 1 degree. So when we rotate the magnetic field for the positron in 1 degree, we expect the positron to start measuring a little bit up, mostly down, but just a little bit up. Right? In the beginning, the magnetic fields are aligned. This is up at 0 degrees, and this is up at 0 degrees, meaning the magnetic field, both of them point up. And since the electron is measured going up, therefore the positron is going to be measured going down, which means 0% of the time will it go up.
Right.
Now, as you change the magnetic field by 1 degree, so what happens?
The positron will go up a little bit, but mostly down.
Right, but I'm trying to rethink what's the logic.
Yeah, this is my question.
Mm-hmm.
How is this practical?
How is this practical? This is either quantum computing works or it doesn't work. This is the next $1 trillion industry. If quantum computing,
I'm saying, like, isn't the idea that the electron and the positron operate a certain way when they're in the same magnetic force, or no?
What?
Like, isn't the reason why the positron goes in the opposite direction is because the electron is there? Or no?
No, they don't communicate.
Or is it because of the magnetic field? They don't have to communicate.
They cannot. If they communicate, then you agree with Bohr. Bohr claims they communicate. If they communicate, that means you're violating the speed of light, because we've seen this done in great distances instantaneously. So the speed of light goes out the window. But also, I mean, this goes back to the superposition. Einstein says that the spin exists. See, what I'm trying to say is that there is a spin. I'm trying to go with Einstein. That there is a definite spin. And it's not working out. And Bohr says there is no definite spin. It's in a superposition. And they decide on the spin when you measure. And they decide simultaneously across the known universe. The universe decides instantaneously across infinite distances what they're going to do. This is called the collapse of the wave function. This collapse happens instantaneously, regardless of the distance between them. That is the theory. That's called the quantum mechanical theory. That's right. So if you look at this diagram, it says hidden variables. The blue line is the Einstein model, and the red line is quantum mechanics. That's the Bohr model. The red line assumes that a particle doesn't have a definite spin until it is measured. It is when it is measured that they both decide on a spin, on some arbitrary spin, opposite each other. But it's only when you measure. And nobody knows what it means to measure, by the way. This thing is completely undefined. And so
we could just say observe, I guess.
No, it doesn't matter. You have to explain.
It don't
to
matter,
me-
yeah.
You have to explain how how the electron knows that I'm observing it. This is nonsense. This is obviously nonsense.
So I get what you're saying. Like, I get what you're saying.
Nothing here makes any sense. It's like I almost had everything figured out, and then this thing Bell's, and then Bell proves that reality cannot be real.
It's not that it's not real. I think that the dependency in reality changes that.
What do you mean? What do you
Like, I would say that now if we're using a Bohr model,
yeah,
the object, it, like you said, is dependent upon the observer instead of like vice versa.
Fine.
So
As far as I'm concerned, that
it
means,
doesn't mean it's not real though.
yeah, that's a definition. That is literally the definition of it's called
But I still think this doesn't prove that 100%. I think it just
it's literally
it needs to be looked more into though.
it's literally
Or the model has that flaw.
It's literally called anti-realism. It has a name. It's called anti-realism. It says this is the peekaboo game, that when the baby doesn't see you, you actually stop existing.
Yeah. And there's no, I still stand by my stance that there is no way to disprove or prove that, regardless.
Well,
even with this model, I think that I see what you mean, but I still don't think
fine. I mean,
there's still no way to prove it.
Yeah, you can. I mean, you can think about it. Let me send you a friend request, because I'm gonna
go make food, so yeah, it's all good.
Let me wait. Where's your profile? There. Got it.
I gotta look more into this to see what's up.
I'm gonna, if you want, I'll give you a ring when I go back to working on this, like tomorrow. Where do you live?
In the U.S.
Yeah, where? Like East Coast, West Coast? Oh, you don't.
East Coast.
East Coast, okay. Anyway, yeah. I'm beginning. I mean, Einstein said that if Bohr is correct, then the universe is full of these connectors. Today they call these wormholes, that every two entangled particles are connected through a wormhole in which the communication is instantaneous. Anyway.
Well,
what?
He might be onto something.
I don't like it. I don't like it.
Oh man,
Einstein
that's a
hated
lot to think about. Though.
Einstein hated this. You don't understand how much he hated it. He would not accept it. Like it's like people, Sean Carroll, who is one of the greatest physicists, he says that the universe, there's an infinite number of universes. Like every time an electron positron pair is observed, the universe gets split in two. So there's
Mm.
an incredible amount of universes being created at every instant in time.
So they don't believe in any objective
They believe in
standpoint of the universe.
they believe in everything that you believe, but they explain it. They need, they need to actually explain it. They need to actually come up with a working model. And I'm trying to come up with a
Mm.
working model. Einstein tried to come up with a working model, but but they've given up on Einstein's hidden variables, on the definite spin. They've given up because they believe that there's no way to avoid Bell's inequality, Bell's paradox. There's no way
Mm.
to explain the curve except for that's it. I mean, the particles are communicating somehow, so that's a given. The question is, how do they do it, or something like that? I don't know. Anyway,
Do they take like
what?
perception of time and space into
You can if you want to listen, I'll give you my favorite physicist. I mean, the people that discuss this are actually physics philosophers. There's a new field that's called the philosophy of physics. It's they study this in philosophy departments.
Hi.
So my favorite guy is Tim Mullen.
Do you go to school for this?
No, you don't need to go to school. I'm very old. Tim Mullen, physics. I'm like,
Yes.
let me see his latest interview. He did an interview.
Correct.
It's exactly when I want the interview that I'm not going to be able to find it. Oh, yeah, it's Earhart or something. Yeah, this guy. Yeah, this was a
The
good
physicists agree
interview.
on the physics, they just don't
So,
agree on what the physical world is like. I
yeah,
mean, that doesn't make any sense. That's what physics is about. It's about what the physical world.
here. No, not that.
Yeah, I'll probably look at this sometime. Like,
So you have two great philosophers here, philosophers of physics. I mean, these guys are both professors of physics and philosophy. And the interviewer is good. So he's a good interviewer. He's just a little bit of an anti-Semite, but we'll forgive him. Anyway,
all right, yeah, I gotta go. I'm about to go make some food.
all right,
I'm
man. I'll
hungry.
see you later. I'll talk to you.
All right, it's cool to talk to you.
Yeah, you too. Bye. All right, we're done. Okay, bye-bye.